Okay, let's keep going here. So this right-hand side, okay, is the I alpha term. Now, looking at this definition again, okay, some moment equals I is alpha, I about the point where you take moment about. This also equals to these two terms. Okay, you can split into these two terms from parallax theorem. First term is the I about center of gravity, alpha, plus MA about center of gravity, okay, MA through center of gravity, times R. And R is the distance between center of gravity and point O. So really, and to be more precise, you should apply this right here, these two terms, twice, one for each object. Okay? So really, this right here, okay, this first term is this, okay, for the wheel, plus the second term, okay, MAG times R. Okay? Second term applied to the wheel. Okay, so this whole thing is for the wheel. However, look at the second term. Second term is mass of B times A, okay, through center of gravity, which is really A at B, times R. What is A at B? Well, point B is not accelerating linearly. Okay? The whole thing is spinning. Okay, so this wheel has an alpha, okay, but it does not have acceleration, okay, linear acceleration. This is 0. And also R is the distance between the center of gravity and the point you take moment about, and they are the same point, therefore R is 0. Okay? So this term is 0 for the wheel. And then for the low A, same thing, I A alpha plus M A acceleration times R. This first term, I alpha, the A itself is not rotating. Okay? It's not spinning at all. This A is traveling along a straight line. Okay? So there's no rotation for the load. So for the load, the only term that has acceleration in it is this linear acceleration term, which is MA times AA, which is the unknown. Okay? Times R, and R is the distance between this line right here and this point. Okay? So, and R is exactly, again, the radius. Okay, so going from this long equation, we can simplify it down to something quite simple. Okay, so left-hand side, we have weight, which is mg, m of A, mg, and times R, equals IB, which is mb times radius of gyration square times alpha plus this other term, ma times the unknown times R. That's it. So this is the equation where you can solve for the unknown A. Everything else is given. Okay? So move all the known quantity to the right hand side. So leaving AA on the left hand side. So we have MAGR minus MBK squared alpha divided by MAR. Now you plug in numbers. Okay? Leave numbers to the very, very last step. MA is 18 kilograms, G is 9.81, R is 600, which is 0.6 meters, minus MB is 144 kilograms, K is 450, which is 0.45 square, times alpha. Okay, alpha is also an unknown, but alpha is related to your A. Acceleration, okay, of point A down here is the same as the acceleration, let's say, at this point. It's also the same acceleration at this point right here. Okay, so this is my AA, the same thing, exact same acceleration. And this acceleration, okay, is related to angular acceleration by a special relationship. So this point, and at this point, is shared by this rope as well as this wheel. Okay, and this wheel follows this curved path, which means that you really have two directions, two components: tangent component of acceleration and normal component. So this AA is really the tangent component of acceleration, which is r alpha. R here is exactly the radius, the wheel. So alpha and A is related by this relationship. So alpha equals AA over R. That's all. So alpha equals AA over R, which is 0.6 meters. Moving on, MA is 18 kilograms times R, which is again 0.6. Now you crunch numbers. Okay, plug in your calculator. Turns out acceleration is 1.7836 meters per second squared. That's all. Okay, so in this problem, you can be asked to find this acceleration of A. Okay, and you might be asked a few other things too. Okay, knowing this acceleration, which is a constant, okay, as you have found. Okay, so this acceleration is true for any position, okay, of this load right here going from here down to here or down to here. It always experiences this exact same acceleration. Okay, starting from rest. Okay, at whatever position, doesn't matter. Right? Now it has this acceleration, so you might be asked to find, for example, the velocity of this load right here after some time, or after it has traveled a certain distance, okay, and things like that. In that case, just bring in the very, very first chapter of the semester, which is kinetics. Okay, so when A equals constant, okay, you have three equations, right? Plus 2A times delta S, right? V equals V naught plus AT, X equals X naught plus V naught T plus 1/2 AT squared, and things like that. Yeah, this is really S, right? This S naught. Okay, so I'm not going to get into that. Alright, so this is another example to illustrate how to solve for acceleration rigid body.